Welcome to this video on the role of solar radiation on the release of dry slab avalanches. Thanks to Thomas Exner and Brad White for their help with this video. I'll discuss both natural and human-triggered dry slab avalanches. Note that this video is about dry avalanches and not the easier to forecast wet avalanches that you sometimes hear crashing over cliffs on a warm spring day. Let's start with the first case study.
This avalanche happened east of Revelstoke, BC around 8:15 on January 18, 2011. That is the Lanark snowshed in the distance. The avalanche pushed trees onto an open highway. Very little snow was deposited on the highway, indicating that only the powder component of the avalanche reached the highway. The highway was immediately closed. Soon after, explosives placed from a helicopter in the Lanark start zone triggered additional large avalanches. Here is the large, complex start zone for the Lanark path. The morning avalanche started here, where the slope faces east and directly caught the sun at dawn. While much of the avalanche followed the gully towards the Lanark snowshed, part of it jumped the gully wall here and ran towards the open highway. The short vegetation shows that avalanches have jumped the gully in the same place in the past. However, in this case, the powder cloud of the avalanche reached the highway and pushed trees onto it. Here is the weather for the 6-day storm leading up to the avalanche. The red vertical line shows when the avalanche occurred. The gray vertical lines are 12 hours apart. The red columns for precipitation, reset every 12 hours, show that about 90 millimeters of water equivalent fell at the precip gauge over the 6 days. The blue and turquoise bars show the average wind speed, which was sufficient to transport snow at times during the storm and at the time of the avalanche. The red and blue lines show the air temperature at the two weather stations at 1600 and 2100 meters. The air temperature at the upper station, which is close to the elevation of the start zone, reached about -3 degrees Celsius. Note the pronounced cooling and decrease in precipitation at the end of the storm. Associated with the cooling, the sky cleared, so the sun would have hit the east-facing slopes for the first time in 6 days. The avalanche occurred about 8:15 in the morning local time, just as the cooling switched to rapid warming. While wind loading of the start zone cannot be ruled out, the local forecasters suspect the first shot of sun on fresh, dry snow was a strong factor in the release of the avalanche. I'll come back to this point about the first sun on fresh, dry snow. In the next couple of slides, I'll float some ideas on why the effect of solar radiation on dry slab avalanche release is difficult and outline the solar warming process. Then I'll summarize a couple of case studies and finish with some ideas on human triggering and making decisions regarding the solar warming effect. So why are we sometimes surprised by the effect of direct solar radiation? 1. We may be in the cold valley bottom when the sun hits the slopes above us. 2. Solar radiation affects the upper snowpack before we notice the obvious signs like the snow surface becoming moist. 3. When the sun comes out after a fresh snowfall, we are thinking, let's head up onto those beautiful snow slopes, and not about a poorly understood process with not so obvious indicators. There is a separate video on the various processes that transfer heat in and out of the snowpack. In this video, I'll only talk about the effect of shortwave radiation on the upper snowpack. When and where the sky is mostly clear, much of the solar radiation from the sun reaches the snow surface as direct shortwave. This direct radiation makes dark shadows with sharp boundaries. Also, sunny slopes get far more radiation than shady or steep north-facing slopes. Whether the shortwave radiation is direct or diffuse, about 90% reflects off a fresh snow surface. So, only about 10% of the shortwave radiation that reaches the snow surface is absorbed. This radiation enters the upper snowpack, mostly reflecting off grains in seemingly random directions. A small part of the radiation is absorbed and warms the grains. If you have ever cut the roof of your snow cave too thin, you realize that you do not begin to see the light, that is, the solar radiation, until you have thinned the roof to about 30 centimeters. So the penetration of shortwave radiation is shallow, mostly less than 30 centimeters, but unlike other warming processes such as warm wind, solar radiation is fast. The rate of warming turns out to be important. So what is our current understanding of the effect of solar warming on the release of dry slab avalanches? Let's focus on natural avalanches for now. I'll use a slide from Thomas Exner's video called Here Comes the Sun. First, fresh, cohesionless snow can become slabby. Also, downslope creep, including slope parallel deformation in the weak layer, will increase and can cause a weak layer to fail, which can release a slab avalanche. The warming front does not need to reach the weak layer. Some of the increased deformation of the near surface layers is transferred to deeper layers. Now, let's look at an experiment by Thomas Exner. Toothpicks, each with a black tip, were placed in a pit wall. The pit wall faced north and the slope faced east. The slope angle was about 45 degrees. The digital camera was set to take pictures every 15 minutes, starting before sunrise. While about 90% of the morning sun would have reflected off the snow surface, let's look at the effect of the 10% that was absorbed. The snow profile on the left shows the snow was below 0 degrees Celsius and soft. I've zoomed in on the pit wall so you can watch the toothpicks move, especially the circled one. The green arrow shows the vertical settlement. The red arrow shows the movement parallel to the slope. Researchers believe that slope parallel shear contributes to the failure of weak snowpack layers. You can use the scroll bar at the bottom of your screen to replay the video. This shows the effect of solar radiation on fresh, dry snow. Obviously, the snow settles, forming a slab. Also, the slab creeps faster downslope, applying additional shear to any weak layers in the upper snowpack. Here is a short case study. On the 24th of March 2012, a graduate student, Cora Shea, and I were doing an overnight study at Chester Lake in the southern Rockies of Alberta. We toured up with our equipment during the night. Dry snow was falling at 1 to 2 centimeters per hour. There was no noticeable wind. We dug our pit, set up our equipment, and started our measurements by headlamp. About an hour before sunrise, the sky cleared and the temperature dropped noticeably. We continued our measurements, eagerly awaiting the arrival of the sun. The site was surrounded by thickets of trees. When the sun hit the top of the first thicket, the fresh, dry snow released as a mini avalanche within a minute. The same thing happened when the sun hit the next thicket of trees. We began to predict when the trees would release the fresh snow. Each time, the snow on the branches released within a minute or so of sun hitting the low-density, dry snow. Perhaps the reason these mini avalanches were so predictable was because the shortwave radiation was penetrating to and warming up the dark needles and branches under the 10 or so centimeters of dry snow. Warming the fresh, dry snow from above and below was likely a factor. Nevertheless, this case study suggests a connection between the predictable mini avalanches of fresh, dry snow when the sun hits the trees with the hard-to-forecast solar-induced dry slab avalanches. Alas, I cheated with the photo. This photo is not of the site near Chester Lake, but nicely shows the fresh, dry snow on thickets of trees. Another case study on a much larger scale occurred in the Purcell Mountains between February 2nd and 5th, 2012. It is well summarized in a video by Thomas Exner called Here Comes the Sun, so I'll jump to the conclusions from that video. 2 factors likely contributed to the avalanche cycle. 1, there was a jump in direct solar radiation when the sky cleared after the storm. 2, there was a well-developed slab and persistent weak layer, which Thomas calls a loaded gun. Now, there was also a rise in the freezing level. However, most of the avalanches during the cycle released on sunny aspects, suggesting solar radiation was the major factor. This seems like a good point to recall Ed LaChapelle's statement. Any rapid change in the mechanical or thermal energy state of the snowpack is a precursor to avalanching, and I emphasize rapid. Solar radiation warms the upper snowpack faster than any other process. So let's summarize the points for natural avalanches. When sun first hits fresh, dry snow, cohesionless snow can become slabby quickly. Also, creep increases, which increases the shear on any weak layers in the upper snowpack, which can potentially lead to slab avalanche release. And with the increase in slabbiness, the potential to propagate cracks in weak layers increases. Okay, now let's talk about human triggering. See the ski tracks? Reports suggest this fatal slab avalanche was triggered where the slab was shallow over the rocks. Photos like this worry me. I wonder how many times I have skied over areas of thin snowpack with a prominent persistent weak layer, but luckily not triggered a slab avalanche. In his PhD thesis, Thomas Exner showed that with warming of the upper snowpack, skier stress penetrates a little deeper. So daytime warming of the upper snowpack has a weak effect on human triggering. However, traveling over thin spot can have a strong effect on human triggering. It doesn't matter whether you're on a skis, snowmobile, or a snowboard. It is always difficult to anticipate triggering of deep slabs from thin areas, but I have even more red flags on a slope with those characteristics when it is receiving direct solar radiation. Here is a thick area of the same slab avalanche that was triggered from a thin area in the last photo. 2 skiers died in the avalanche. So how can these case studies and theory help us make better decisions? First, let's recognize the effect of solar radiation on dry slab avalanching is difficult to anticipate. We have access to quantitative forecasts for precipitation, air temperature, and wind, but in most situations, not for solar radiation. Other factors like a warm wind can contribute to instability, but these are slower to warm the upper snowpack than solar radiation. And we know that rapid warming can contribute to slab avalanching. Two situations seem to require extra caution. One, a substantial increase in direct solar radiation combined with an existing slab and persistent weak layer. Note that we're still talking about a dry or mostly dry snowpack. Two, the first shot of direct solar radiation on fresh dry snow. In a survey of experienced avalanche practitioners, Thomas Exner found that more surprises occurred on slopes that faced east or southeast. I suspect the warming from direct solar radiation is faster in the east quadrant in the morning than on the west quadrant later in the day, but there's a fine research topic.
For more on solar radiation and dry slab avalanches, you can search the web for these keywords. In addition to Thomas Exner and Brad White, who helped with this video, I'm grateful to these folks for sharing their insight into the effect of solar radiation on the upper snowpack and on dry slab avalanches.